So another thing to keep in mind when you're doing integration questions, which can sometimes help, is to look at the symmetry of the function. Okay? So if we've got some function f, which is continuous on some interval from negative a to a, so negative a is over here, a is over here. Same thing with, let's say, this one here. This is negative a, and this would be a. A function is said to be even if f at negative x equals f at x. So at this point here, let's say we take a random point here, like here. We'll call this x. This is minus x. It's the same distance on 0. We notice that the values of our function are exactly the same. Okay? So this function is even because it's symmetric about this line y equals 0. The function is odd if we pick these points. Let's say we pick x here and negative x right here. We notice that the value of the function is going to have the same magnitude but the opposite sign. So f at negative x equals negative f at x. So this is an odd function. It's what we call anti-symmetric around the x-axis, the y-axis, or the line y equals 0. What if we want to do an integral? Okay, let's say we are integrating this function from negative a to a. Okay. Well, let's just think about it in terms of the area underneath the curve. If we look at this even function in terms of the area that we want, we can divide it nicely in half. We've got the area from negative a to 0, and then the area from 0 to a. Those two areas are exactly the same shape and exactly the same size. And they're both above the x-axis, so they're both positive areas. So for an even function, this integral from negative a to a of our function f at x dx is equal to 2 times the area from 0 to a of our function. Okay? So we can do half of this integral from 0 to a and then just multiply it by 2 because we know that this is a symmetric function. Okay? What's going to happen for our odd function? Well, if we're integrating from 0 to a, the areas that we're interested are going to be sort of this area here and this area here. What do we know about these two areas? Ian. They're going to add up to 0. They're going to be the same size, but one of them is a positive area because it's above the x-axis. The other one's a negative area because it's under the x-axis. So if they ask you to integrate an anti-symmetric or an odd function from negative a to a, you know that the answer that you are going to get is just going to be 0. Okay? So that can sometimes save you a lot of time. Okay? So in case you don't believe me, let's do an example here. We want to do the integral from negative 2 to 2 of the function x squared plus 1. Oh, sorry, x to the 6 plus 1. First off, is this an even function or is it an odd function? Yeah, it's even. How did you know it was even? What do you think? Hayden? The exponent is even, yeah. And if you want to check, you can always do something like figure out what f at negative x is. So if I put negative x in there for x, well, let's see. Negative x to the power of 6 is just going to be the same as x because it's an even exponent. So negative x to the 6 plus 1 is equal to x to the 6 plus 1, which is equal to f at x. So we've got an even function here. So how would you set up this integral here? Well, we're not talking about areas here. We're just doing an integral. So the integral from -2 to 2 of x squared plus 1 dx is going to be equal to, using the properties from the previous slide, 2 times the integral from 0 to 2 of x to the 6 plus 1 dx. Oh, that is x squared plus 1, and it definitely shouldn't be, should it? It should be 6. Okay? So we'll keep that constant out front, and we'll do our antiderivative here. X to the 6th is, let's see, the antiderivative is going to be something to the 7th, 1 over 7th, plus antiderivative of 1 is just x. And then we want to evaluate this from 0 to 2. Why has doing this made our integral a little bit easier? Because now one of our limits of integration is x equals 0, and it's super easy to evaluate this function at x equals 0. So we are going to have our function, well, sorry, our antiderivative here, evaluated at 2, okay? And then we would subtract this function evaluated at 0, but we know it's just going to be 0. So we just have to really evaluate at one of our limits here. So we get 2 times 1/7 times 128 plus 2, and we can work out what this is, and it all works out to 284 over 7, exactly. So that's getting a common denominator, and et cetera, et cetera, et cetera. Okay?